The Boötes Void is 330 million light-years across. It contains 60 galaxies. It should contain thousands. Astronomers call it the closest thing to hell we have ever mapped. What does it mean that emptiness is the universe's default state? In 1981, 4 astronomers were working through a routine survey at Kitt Peak National Observatory in Arizona. Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman were not looking for anything strange. They were counting galaxies. The method was straightforward. Point the telescope at a patch of sky, expose a photographic plate, develop it in the darkroom, and count the smudges of light. Each smudge was a galaxy. Each plate covered an area roughly the size of a full moon. In a universe of average density, a field that large should contain thousands of galaxies. The first plate came out wrong. It was nearly blank. Not dark from an error, not overexposed. The emulsion was perfect, the tracking was correct, the sky was clear. There were simply no galaxies on it. A few specks, lonely, isolated. The kind of scattering you would expect in a randomly chosen patch of deep space if the universe were a desert, which it is not supposed to be. They ran the exposure again. Same result. Then another field, adjacent to the first. Same. Then 10 plates. The pattern held. Where the catalogues predicted a dense city of galaxies, there was a blank wall. Kirshner later described the sensation in exact, unnerving words. We kept looking. We'd point the telescope, expose the plate, develop it in the darkroom, and there was nothing. Just a few scattered, lonely specks. It was like looking at a map of a city and finding a neighborhood where the buildings had all been erased. The astronomers had not found a gap. They had found a hole, a region where galaxy formation had effectively not happened, or had been suppressed so completely that the result was a near-perfect absence. The numbers took time to sink in. The void they mapped spans roughly 330 million light-years from edge to edge. Light itself, racing at 186,000 miles per second, would need 330 million years to cross it. To put that into a shape your mind can hold, if you place the entire Milky Way at one boundary of this void, you would need more than 3,000 Milky Ways lined up side by side to reach the other side. Inside that volume, astronomers expected to find approximately 2,000 galaxies. They found 60, not 60 bright ones with fainter companions. 60 total. The deficit is not a statistical wiggle. It is an obliteration. The galaxies that do exist inside the Boötes Void are isolated to a degree that is hard to process. The average separation between them is so vast that if an intelligent species arose on a planet orbiting one of those lonely stars, its astronomers would look out into a night sky almost entirely dark. No neighboring galaxies, no grand spirals hanging in the blackness, just a few faint, distant specks, and beyond them, nothing. They would believe themselves alone in the universe, and they would be closer to right than we are. Kirshner carried the psychological weight of this discovery into his teaching. He reportedly told students, "It's the closest thing to hell we've ever mapped." The word matters. He did not say the most surprising thing or the most puzzling structure. He said hell, and he was not being dramatic. He was naming a specific kind of dread, the shock of confronting a place that should be full of burning galaxies, and finding instead a silence so deep it feels like deletion. Hell, in this definition, is not fire. It is absolute emptiness, not a place of torment, but a place of absence so complete that existence itself appears to have been withdrawn. What makes the Boötes Void truly disturbing is that it was not a fluke. As survey technology improved through the 1980s and 1990s, as a Sloan digital sky survey began to map the three-dimensional positions of millions of galaxies, a pattern emerged that was more chilling than any single void. The voids were everywhere. They were not anomalies scattered through a populated cosmos. They were the dominant structure. The filaments of galaxies, the dense clusters, the bright walls where stars congregate, these are the exceptions. Filaments and walls and clusters occupy perhaps 5% of the universe's volume. The voids occupy the remaining 95%. Read that again and let it settle. Most of the universe, by volume, is not the star-filled space we see when we point our telescopes upward. It is the blank plates from Kitt Peak, repeated in every direction, at every scale. Emptiness is not the interruption between galaxies. Emptiness is the baseline. The galaxies are the interruption. This discovery forces a question that will not let go. If emptiness can be this absolute, a hole where thousands of galaxies should burn, a region so stark that the astronomers who found it reached for the language of damnation, then what else is out there beyond the familiar glow of the Milky Way? And what does it say about our own place if we are not floating above the void, safely distant, but might already be inside one? Your galaxy is not a ship on an open sea. It is a docked boat in a harbour you have never seen. The harbour is called the local group. It is a gravitationally bound collection of approximately 50 galaxies, stretched across a region 10 million light-years in diameter. The two largest boats are the Milky Way and Andromeda, spirals dominating a scattered fleet of smaller, irregular and dwarf galaxies. You learned to picture the Milky Way as a lone city of stars adrift in the void. But you were never adrift. You are moored. The harbour is small, provincial, a minor hamlet in the architecture of the universe. Pull the map back further. The local group does not sit in isolation. It rests at the periphery of the Virgo supercluster, a sprawling structure of galaxy groups and clusters that extends roughly 110 million light-years. The Virgo supercluster contains thousands of galaxies, immense swarms of hot gas, dark matter halos woven through the spaces between them. The local group is a minor outpost on its fringe, not a capital, not a centre, an edge condition. Even this giant is only a lobe of something far larger. In 2014, astronomer Brent Tully and his team stood before a room in Honolulu at a meeting of the American Astronomical Society. They had spent years mapping the velocities of galaxies, tracing their movements through space like hydrologists tracing currents in an ocean. What emerged was a structure so immense it swallowed the Virgo supercluster whole. They called it Laniakea, Hawaiian for immense heaven. On the screen, a map appeared. Blue filaments, orange knots, a cosmic watershed 500 million light-years across, containing the mass equivalent of 100 million billion suns. Tully placed a pointer on a tiny dot, a speck on the outer edge of one filament, and said 5 words that rewired the room. "That's us, the Milky Way." He paused. "We're not downtown. We're in the suburbs. And we're falling." A journalist present later wrote that the room applauded, but the sound was hollow. A well-known astronomer had just pointed to a blue speck on a giant screen and told the audience that everything they thought about their cosmic address was a provincial fantasy. The Milky Way is not a central figure in the drama of the universe. It is a minor character in the outer chapters of a supercluster whose real action is somewhere else. This moment was not a gentle correction, it was a demotion. The Virgo supercluster, which once seemed like the largest relevant structure, was downgraded to a lobe. The local group, our harbour, became a backwater dock. And the Milky Way, our galaxy, the entire theatre of every human thought and war and prayer, became a dot on a filament, barely within the gravitational watershed of Laniakea. And then Tully said the second thing. "We're falling." Falling toward what? A gravitational centre called the Great Attractor. Every galaxy in our region, including the Milky Way, including Andromeda, including the entire local group, is being pulled toward this hidden concentration of mass at a velocity of approximately 600 kilometers per second. That is 2 million miles per hour. You are at this moment moving sideways through intergalactic space at a speed that defies instinct. It is not a drift, it is a flood. A river of galaxies, all pouring toward a destination we cannot directly see because the dense plane of the Milky Way's disk blocks the view. The great attractor lies behind the zone of avoidance, a blind spot in our map created by our own galaxy. The thing that pulls us hides behind our own stars. That is not a metaphor. That is a physical fact. Carl Sagan in 1980 spoke a line that has since been repeated until it lost its edge. The universe is a pretty big place. If it's just us, seems like an awful waste of space. The line was originally delivered with a kind of wry wonder, a nudge toward humility. But now it lands with a cold new weight. We are no longer talking about a big place as an abstract idea. We have the map. Laniakea stretches 500 million light-years, and we are a dot on its periphery. The space around us is enormous, and the waste Sagan described is not a poetic observation. It is a measurement. The void-dominated universe we have already glimpsed, the emptiness that is the default condition of space, extends in every direction from our suburban dock. And we are inside that emptiness, not floating above it. This is the first displacement. The Milky Way is not where you thought it was. It never was. The image of a lone galaxy adrift in a sea of stars was a parochial story, told by a species that had not yet seen the map. Now the map exists, and the dot on it is small, and the dot is falling. The Boötes Void was not a fluke. Through the 1990s and into the early 2000s, a quiet revolution was unfolding in astronomy. The Sloan Digital Sky Survey, a project that would eventually map over 1 million galaxies in 3 dimensions, began releasing its data. For the first time, astronomers could trace not just the positions of galaxies on the flat plane of the sky, but their depths, their distances, their relationships to one another across billions of light years. What emerged from the numbers was not the uniform sprinkle of galaxies that textbooks had trained everyone to expect. It was a skeleton, a web. The universe, seen in full, organized itself into thin filaments and broad sheets of galaxies. These structures are not metaphors. They are physical, coherent chains of galaxy clusters connected by bridges of dark matter and hot gas stretching across hundreds of millions of light years. Between them sit the voids, the bones and the hollows, the threads and the gulfs. And the proportions are brutal. The filaments and dense walls, the regions where galaxies cluster, where stars form, where light has something to reflect off, occupy roughly 5% of the universe's volume. 5%. That is the sum total of what we once mistook for everything. The remaining 95% belongs to the voids. Hold that number. Not as poetry, as geometry. If you were to select a random point in the universe, truly random, not weighted toward any galaxy or cluster, the odds are 19-1 that you would land in nearly complete emptiness. No stars, no planets, no light sources of any kind beyond the faint stretched glow of the cosmic microwave background. The dominant experience of existing in this universe, at the largest scales, is not fire. It is absence. The surveys did not just reveal the voids. They revealed that the voids are the rule. Yet the voids are not entirely empty. They contain dark matter, still present, but at lower densities than in the filaments. They contain a handful of isolated galaxies, stragglers, that somehow overcame the odds and ignited alone in the dark. But the formation of galaxies was suppressed inside these regions from the very beginning. The same quantum fluctuations that existed in the infant universe, the tiny density variations, imprinted fractions of a second after the Big Bang, seeded both the overdensities that became clusters and the underdensities that became voids. Where density was slightly above average, matter collected, collapsed, and lit up. Where density was slightly below average, matter never gathered in sufficient quantities. Galaxy formation never truly began. From the moment the universe cooled enough to even contemplate structure, most of space was already doomed to be hollow. The Boötes Void is one example, the one that broke the human imagination first. But it is not the largest. In 2013, the same year that the Hercules Corona Borealis Great Wall was announced, a team led by Ryan Keenan, Amy Barger, and Lennox Cowie proposed the existence of a void so vast that it makes Boots look provincial. They called it the KBC Void, using their initials, and estimated its diameter at roughly 2 billion light-years. 2 billion light-years. A region of space so large that light, racing from one end to the other, would need 2 billion years to complete the journey, nearly a sixth of the entire age of the universe. And the KBC void may contain us. If the hypothesis is correct, the Milky Way does not sit near a void, it sits inside one. Our entire local group, our harbour of 50 galaxies, is a minor condensation embedded within an underdensity that spans a significant fraction of the observable universe. The emptiness we have been staring at through telescopes, the hole in the constellation Boötes, the blank spaces on the map. Those were not distant warnings. They were mirrors. Think of the universe as foam. The filaments and clusters are the thin walls of soap, curved surfaces where all the light and structure and complexity have gathered. The voids are the bubbles, vast, dark, making up nearly all the volume. The walls may shimmer with galaxies, but the bubbles dominate the architecture. The Milky Way is a speck on one such wall, clinging to the skin of an emptiness that extends in every direction beyond our ability to compress into language. Surrounded on all sides by darkness so complete it swallows meaning. This is the architecture already woven around us before any question of life, of signals, of contact. And if life requires stars, requires galaxies dense enough for chemistry to iterate across billions of years, then life is concentrated in those thin soap walls. The filaments, the 5%. We reside on the edge of a void, in the suburbs of a supercluster, in a region where star density is lower than the cosmic average. The silence we hear from the cosmos, the famous quiet that has haunted astronomers for decades, may not be a mystery to solve. It may be the natural acoustics of an address designed by emptiness. The signal from the dense neighbourhoods, from the filament cores, where galaxies crowd together, would have to cross hundreds of millions of light-years of near-nothing to reach us. And the space between is growing. The foam is not static. The bubbles are expanding. The walls are thinning. Every second, the architecture that makes our address a backwater is pushing the dense regions farther away, stretching the already impossible distance between a whisper and an ear. Go back to the night it happened. Kitt Peak National Observatory, Arizona, 1981. Robert Kirshner, Augustus Omler Jr., Paul Schechter, and Stephen Schechtman were running a routine survey. The method was mechanical by then. Point the telescope at a patch of sky, expose a photographic plate, develop it in the darkroom, count the galaxies. Repeat. They had done this hundreds of times. They knew what a plate should look like, dusted with thousands of tiny elliptical smudges, each one a galaxy, each one containing hundreds of billions of stars. A full moon's worth of sky should have been crowded with them. The first plate came out wrong. They assumed an equipment failure, a bad exposure, something chemical in the developer. They checked everything, recalibrated, and shot again. The second plate matched the first. So did the third, and the fifth, and the 10th. Every plate covering that same patch of sky in the constellation Boötes showed the same thing, almost nothing. Where several thousand galaxies should have been burning, There were perhaps 60. Lonely specks scattered across an otherwise blank field. The astronomers were not looking at a region of low density. They were looking at a deletion. Kirshner later described the sensation of standing in front of a map of a city and finding a neighborhood where every building had been erased. Not bombed, not abandoned. Erased, as if the city had never been planned there at all. The void was not quiet space between clusters. It was an active absence, a volume where structure itself had been vetoed. He said it plainly, years later, in a voiceover, while staring at a three-dimensional map of the survey data. His words were measured. It wasn't just empty, it was a hole in the universe. And we were sitting inside it, looking out. Sitting inside it. That is the phrase that catches. The void was not somewhere else. From the perspective of the light arriving at Kitt Peak, the hole surrounded them. The plates were windows into a negation that wrapped around the observatory, around the Earth, around the entire Milky Way. They had discovered an emptiness so absolute that the human mind, sensing it, instinctively placed itself inside the wound. Now let the numbers do what words cannot. The Boötes Void spans roughly 330 million light-years across. If you place the entire Milky Way at one edge, all 100,000 light-years of it, every spiral arm, every star cluster, every nebula, you would need over 3,000 Milky Ways lined side by side to reach the other side. Light itself, the fastest thing in existence, racing at 186,000 miles per second, needs more than 330 million years to cross this volume. That is longer than the time it took for the first land plants to evolve on Earth. Longer than the entire reign of the dinosaurs. A beam of light that entered one side of the Boötes Void, when the first vertebrates crawled out of Earth's oceans, is still travelling. It has not yet emerged. Inside this chasm, the 60 known galaxies are not clustered. They are marooned. The average distance between them is so immense that if an intelligent species arose on a planet orbiting a star in one of those isolated islands, its astronomers would look out through their telescopes and see almost total darkness. No spiral neighbours hanging in the sky, no bright galactic cores, no faint smudges of light indicating other islands of matter. A permanent, starless black stretching in every direction, broken only by the few dim stars of their own lonely galaxy. They would scan the heavens and conclude they were utterly alone, and they would be right. Not existentially, geometrically. The nearest other galaxy would be too distant to resolve with the naked eye. The cosmic web, the filaments, the great walls of clusters, all of it would be invisible. Their entire observable universe would be a single mote of light in an ocean of nothing. They would build telescopes, map the void, and perhaps, like us, discover they were living inside a hole. The difference is, their hole would be all they could ever see. Kirshner's remark to his students has been repeated many times. Its power does not come from poetry. It comes from precision, he said. It's the closest thing to hell we've ever mapped. He was not talking about fire. The oldest visions of damnation were hot. Lakes of flame, burning sulphur, unending pain. But that at least is something. Fire is a presence. Heat is a sensation. The Boötes Void offers neither. Kirshner's hell is a condition of total silence, total isolation, total absence, stretching in all directions without limit. Not punishment inflicted by a tormentor, just the permanent, irreversible failure of anything to exist. When you stare into the Boötes Void, you are not seeing a place waiting to be filled. You are seeing a region where formation itself was stillborn. The quantum fluctuations that seeded every galaxy you have ever seen, the Milky Way, Andromeda, the Virgo cluster, had an equal and opposite expression. Where density tilted slightly above average, structure condensed and ignited. Where density tilted slightly below average, nothing could gather. The void is not an accident. It is the other half of the equation. The negative image of existence. That is what makes it feel malevolent. Not because it wants anything, because it doesn't. The void is not hostile. It is indifferent to the point of erasure. The same physics that lit the stars also drew a blank here, and the blank is 330 million light-years wide. Now bring that thought back to where the previous section left you. The universe is 95% void by volume. The Boötes Void is the most famous example, but it is not an outlier. It is a representative sample of what most of reality actually is. The filaments, the walls, the clusters, the places where light exists, where chemistry happens, where life could conceivably ask a question, are the exception. Emptiness is the default. If emptiness on this scale is the closest cartography has ever come to mapping damnation, then the universe begins to look less like a creation and more like a tomb. Not a tomb that was filled and then sealed, a tomb that was built empty and never occupied. 95% of its volume is already dead ground. And if you recall what was revealed about the KBC void, the underdensity that may span 2 billion light-years and may contain the entire local group, then the horror shifts orientation. The Boötes Void is not somewhere we are going. It is a portrait of the kind of place we might already inhabit. The question is no longer why the whole exists out there. The question is whether we have been buried inside our own. The map that bent the room was not drawn by hand. It was etched by velocity. In 2014, Brent Tully and his team did not simply count galaxies and plot their positions. They measured how fast each one was moving, added its trajectory, and traced the lines of flow like cartographers following rivers downhill. What emerged was not a static atlas of objects, but a dynamic portrait of motion, a vast gravitational watershed they named Laniakea, a Hawaiian word meaning immense heaven. On the screen at the American Astronomical Society meeting in Honolulu, the structure materialized in blue filaments and orange knots, a supercluster 500 million light-years across, containing the mass equivalent of 100 million billion suns. Galaxies were not randomly scattered within it. They were all sliding in the same direction, funneled along invisible channels toward a single, unseen point. Tully raised a pointer and aimed it at a minuscule dot on the outer edge of one filament. His words were calm, untheatrical. "That's us, the Milky Way. We're not downtown. We're in the suburbs. And we're falling." A journalist present wrote that the room applauded, but the sound was hollow. The dot was not stationary. It was already in motion. The gravitational center toward which everything in Laniakea streams is called the Great Attractor. It sits behind one of the most frustrating blind spots in observational astronomy, the zone of avoidance. The dense plane of our own galaxy's disk, thick with stars, dust and gas, blocks visible light from that direction, obscuring whatever lies there like a curtain drawn across a window. We know the attractor contains a massive concentration of galaxies, the Norma cluster, embedded in an extensive filament of dark matter. But its full mass, its full extent, remains hidden. We are being pulled by something whose shape we cannot trace. In 2019, astronomer Stacey McGarr was using the 64-meter radio dish at the Parkes Observatory in Australia to cut through that glare. Radio wavelengths pierce the dust better than visible light, allowing velocities to be measured even when the objects themselves are obscured. A visiting filmmaker was present as McGarr monitored the data stream. He turned from the screen and said, without drama, as if reciting a weather report, "Every galaxy between here and that point, thousands of them, is moving. We can measure it. 600 kilometers per second. That's 2 million miles an hour. We are, right now, as you're sitting in this chair, falling sideways into a thing we can't see. 2 million miles an hour. The figure is too precise to feel abstract. Translate it. Since the moment you began reading this sentence, the entire Milky Way has covered more than 500 miles in the direction of something invisible. Andromeda is moving with us. The entire local group, 50 galaxies, is in the same current. The Virgo cluster, thousands of galaxies more, is not exempt. They are all sliding, pulled along the same gravitational gradient, funneling toward the attractor at velocities that defy the image of a slow cosmic drift. This is not a drift. It is a flood. The galaxies are not gracefully orbiting a stationary core. They are hurtling through intergalactic space as part of a river whose banks we cannot see. The local group is not a ship at anchor. It is a vessel caught in a current that has been flowing since before the Earth existed. And we, every star, every planet, every living nerve, are on board. The measured pull of the great attractor is too strong for the visible matter we can account for. Even after adding the Norma cluster and every galaxy we have identified behind the zone, the numbers do not balance. The gravitational deficit is enormous. Dark matter is invoked, as it almost always is, to fill the gap, but its distribution in that direction is uncertain, modelled rather than mapped. The attractor is, by definition, a thing we cannot fully see, exerting a force sufficient to drag an entire supercluster. Now comes the final weight. We will never reach it. The expansion of the universe is not paused by gravitational attraction. Space itself stretches relentlessly, and that stretching is accelerating. The great attractor pulls us toward it at 600 kilometers per second, but the space between us and it grows faster still. Every second, the finish line recedes. The fall is real, measurable, unstoppable, and perpetually unfinished. A river that rushes forever downhill, but never finds the sea. The gradient is there. The motion is there. The destination is there, exerting its silent claim. But the riverbed lengthens faster than the water can flow. We are that river. The Milky Way, Andromeda, the thousands of galaxies in our basin, all of them streaming toward a point that will remain forever beyond reach. The motion is eternal. The destination is a ghost that recedes at the pace we pursue it. And we cannot turn off the current. The 2019 measurements at Parkes continued into the evening shift. The 64-meter dish was tracking a cluster near the far edge of the Laniakea flow, one of the outermost objects whose light carries information about the attractor's grip. The numbers arriving were not ambiguous. They were wrong. A technician watching the data stream noticed it first. The velocity of that distant cluster did not sit where the gravitational models predicted. It was not slightly higher. It was higher enough to register as a deviation, an outlier beyond the smooth curve of a constant pull. The cluster was moving faster than it should. If gravity were a steady hand drawing galaxies inward, the speed at a given distance should hold a specific value. This cluster had broken the curve. Stacey McGarr leaned forward in his chair. The remark that followed was caught on film by the visiting documentary crew, and it has circulated since as a crystallizing moment, not because it answered anything, but because it dropped the pretense that the standard explanation was sufficient. That's not good. If the acceleration is increasing, that means it's not just gravity. There's something else. Something we're not accounting for. The words were spoken quietly, without flourish. They did not need ornament. They meant that the most powerful engine of motion in our cosmic neighborhood might not be what we had assumed. The standard model of the great attractor is clean in principle. A massive concentration of galaxies and dark matter sits at the gravitational center of Laniakea. Everything within the basin falls toward it. The longer the fall, the more speed accumulates. Predictably, governed by the same laws that dictate an apple dropping from a branch. Constant acceleration from a constant source. Simple, reassuring. But if the acceleration is not constant, if galaxies near the outer edge are speeding up at a faster rate than the inverse square law permits, then something is wrong at the root. One possibility is that dark matter is distributed not evenly, not in a smooth halo, but in a way no model currently captures. Perhaps the attractor's mass is not a single lump but a gradient of concentrations, like submerged ridges in a riverbed that accelerate the flow unpredictably. The dark matter would have to be arranged in an exotic geometry, and we have no direct way of testing that arrangement from behind the zone of avoidance. Another possibility is more unsettling. The extra acceleration might not be gravity at all. Dark energy is understood as a property of space itself, a repulsive force that drives the expansion of the universe, growing stronger as the voids between galaxies deepen. But what if dark energy does not behave uniformly everywhere? What if its effects are modified in the presence of immense gravitational potentials, introducing a force that adds to gravity's pull instead of opposing it? No working theory fully describes this. The hint is too thin, the data too sparse, to build a new physics upon. But the hint exists. Then there is the third possibility. We are wrong about gravity at large scales. The laws that govern falling apples and orbiting planets might be a local approximation of something more complex. Modifications to general relativity, theories like MOND or its relativistic extensions, have been proposed for decades to explain galaxy rotation curves without dark matter, and they have struggled to account for cluster-scale observations. Yet an anomaly at the scale of a supercluster flow, where accelerations are 1,000,000 times smaller than inside galaxies, opens a door that was never fully closed. If gravity itself deviates from the Newtonian prediction across hundreds of millions of light years, then the great attractor is not a hidden mass pulling us. It may be a hidden regime of physics. The zone of avoidance compounds every uncertainty. The dense plain of the Milky Way's disk, the river of stars, dust, and gas that traces the galactic equator from our vantage point inside it, sits directly between us and whatever lies at the gravitational center of Laniakea. Visible light telescopes cannot pierce it. The core of the attractor, the Norma cluster, and whatever else resides at that gravitational center, is a shadow shape inside a bright fog. Radio and infrared observations cut through the dust partially. The Parkes dish and its counterparts around the world measure velocities by the shift of 21-centimeter hydrogen lines, by the microwave glow of heated dust, by the X-ray halos of hot gas in clusters. But these are fragmentary glimpses. We are reconstructing the engine from its exhaust trails, inferring the mass and position of a structure we cannot photograph directly. The geometry we assign to the attractor is a best fit, not a direct reading. If the best fit is missing a major structural element, a second massive cluster, an unexpected dark matter ridge, an entire filament behind the galactic plane, then our estimate of the gravitational force is systematically low, and the anomalous acceleration is a phantom created by our own incomplete map. The other possibility is that the map is not just incomplete. It may be fundamentally misreading the architecture. Consider what it would mean if the acceleration is physically real. Galaxies across the Laniakea basin would be not simply falling. They would be falling faster over time, as if the source of the pull were strengthening or an additional force were coming online. The river analogy breaks here. A river's current is steady, or it slows as the gradient flattens. This would be a river whose gradient steepens the further you travel, as if the sea were pulling the water forward with hands that grow stronger with distance. That is not gravity as we understand it. That is something we cannot name. The open question is not just academic. It is a crack in the foundation of every motion we have mapped. If an unaccounted force exists, dark energy expressing itself in the dense regions, a modification of gravity, a structure more massive than any supercluster we have classified, then the maps of Laniakea are provisional. The flow lines that Tully traced in 2014, the graceful arcs of blue filament and orange knot, might be incomplete interpretations. The entire basin, and our galaxy's place within it, would be subject to forces we cannot control and cannot yet describe. And still the zone of avoidance keeps its secrets. The Milky Way blocks our view of the engine that drags us. We cannot step outside the plane of the galaxy to look back. Every observatory ever built sits inside the fog, straining through it with instruments that were never designed to fully penetrate this particular wall. The Norma cluster is likely not the whole answer. What lies deeper, behind the cluster, behind the dust, behind the limit of even radio and infrared, is simply not known. The uncomfortable truth is not that we are falling. That was already established. The uncomfortable truth is that we are falling into a phantom whose nature may be partly or entirely misperceived. The thing that pulls us toward the basin of Laniakea is hidden, possibly not gravity in the form we trust, possibly not a simple mass concentration, possibly not even a single coherent object. Its real nature may be something we never resolve. We do not know what is dragging our supercluster. We do not know if the force is constant or changing. We do not know if our maps are minor revisions away from the truth or fundamentally wrong. And the blind spot that hides the answer is not a temporary obstacle. It is built into our address, a permanent condition of living inside a galaxy that faces the wrong way. The attractor will remain a phantom, and our fall will remain a mystery, long after every other piece of this puzzle has been assembled. In 2013, while the world's attention flickered elsewhere, 3 astronomers published a paper that should have landed like a detonation. Ryan Keenan, Amy Barger, and Lennox Cowie had been examining galaxy distributions across billions of light years. They were not hunting for voids. They were conducting a census, expecting to refine the standard picture of cosmic structure. What they found was something the standard picture could not comfortably contain. The galaxies around our own, the local group and its neighbours, were not sitting in an average region of the universe. They were inside a depression, a basin, an underdensity so large that its boundary eluded easy measurement. The team gave it a name assembled from their initials, the KBCC Void. Its estimated diameter was roughly 2 billion light-years. 2 billion light-years. That is not a gap between clusters. It is a volume that would take light longer to traverse than the entire history of life on Earth. Longer than the Cambrian explosion, the dinosaurs, the rise of mammals, and every human civilization stacked end to end. Inside this sphere, matter density runs approximately 20% below the cosmic average. The deficit is not a statistical flicker, it is a chasm. When cosmologists run simulations of how structure emerged from the early universe, voids of this scale appear rarely. The physics of quantum fluctuations, imprinted during inflation and amplified by gravity over billions of years, produces a characteristic distribution of dense and underdense regions. Voids are expected, but the KBC void sits at the extreme tail of that distribution. Some calculations place its statistical probability below 1 in 1,000. That is a 10 sigma deviation from average density, a value so unlikely that you might not expect to find a single example in the entire observable universe. Yet here we are, inside one. The near central position of the Milky Way within this void adds a second layer of statistical discomfort. If the void is real, our galaxy does not merely reside within it. It sits close to the middle. Standard cosmology does not forbid a galaxy occupying the center of a large void, but it does not favor it. The most natural locations for galaxies are in the filaments and walls, where the gravitational confluence of dark matter draws baryonic gas into star-forming pools. The center of a void should be the last place to find a bright spiral galaxy with a complex planetary system and a species-building telescopes. The probability, taken at face value, is uncomfortable enough to force a choice. Either such large voids are more common than our models predict, which means the models are wrong at a fundamental level, or we are the beneficiaries of a coincidence so extreme it verges on the absurd. The third possibility, unspoken but present in every skeptical paper since 2013, is that the void itself is an artifact of incomplete data, a mirage generated by surveys that have not yet mapped enough galaxies to fill the supposed emptiness. But the consequence of even entertaining that possibility is stark. We do not know whether the largest nearby structure in the universe is real or a ghost. The implications reach immediately into the most tense debate in modern cosmology. For nearly a decade, two methods of measuring the expansion rate of the universe, the Hubble constant, have produced conflicting answers. Measurements based on the cosmic microwave background, the ancient light from the early universe, give a value near 67 kilometers per second per megaparsec. Measurements using Type Ia supernovae and other local distance indicators give a value near 73. The discrepancy is not minor. Error bars on both measurements have shrunk to the point where the tension is now a rupture. A 5 sigma disagreement that either signals new physics or a hidden systematic error. Enter the KBC void. If the Milky Way and its local neighborhood sit inside a vast underdensity, then the space around us is emptier than the universal average. Emptier space expands faster. Gravity from dense regions slows expansion locally. In an underdense region, expansion meets less resistance. The Hubble constant we measure from nearby supernovae would therefore not represent the true cosmic rate. It would read high, specifically higher than the value imprinted in the cosmic microwave background, which averages over the entire observable volume. The void hypothesis does not require new particles. It does not need dark energy to behave differently over time. It simply states that we have been measuring expansion from inside a bubble, and the bubble distorts our reading. The Hubble tension in this view is not a sign of physics beyond the standard model. It is a sign that we calibrated our instruments in a cosmic desert and mistook local conditions for universal law, that is, the elegant resolution. But elegance in cosmology rarely comes without a cost. If the KBC void explains the Hubble tension, it does so by revealing that our entire observational window is warped. Every distance we have measured using standard candles, Cepheid variables, Type Ia supernovae, tip of the red giant branch stars, is calibrated against a local volume we assumed was representative. If that volume is underdense, the calibration is tilted. The true size of the universe, the true age, the true distribution of matter, all of it shifts. The KBC void transforms from a curiosity into a permanent asterisk attached to every cosmological fact we have ever asserted. We are not looking at the universe from a neutral vantage. We are looking at it through the curved glass of our own address, and we cannot remove the glass. The void is not a distant object like the Boötes chasm, which we can point at from outside and measure with cold precision. We are inside it. We have always been inside it. The emptiness is not a feature on the map. It is the map. Every galaxy we observe, every supernova we clock, every redshift we convert to a distance passes through the filter of the local underdensity. The Hubble constant we measure is not wrong in a simple sense. It is accurate for our location. It is simply not the universe's number, and we cannot step outside to check. No spacecraft will ever cross the boundary of the KBC void to take a reading from true average space. The edge, if it exists, lies a billion light-years away. The expansion of the universe ensures that even a signal sent from that boundary would take longer to reach us than the remaining lifetime of the Sun. We are sealed inside the bubble. The bubble is all the data we will ever have. The recognition settles slowly. The void is not simply a region we happen to inhabit. It is the medium through which every photon of extragalactic light has travelled to reach our telescopes. It is the baseline we mistook for neutral. And if the void is real, if the 20% deficit is not an artifact, if our position is not a computational error, but the actual architecture of our cosmic neighbourhood, then the lens we thought was clear has always been curved. Every Hubble diagram, every distance ladder, every inference drawn from the apparent brightness of distant supernovae. The universe would appear to expand faster here than elsewhere. Not because new physics is at work, because our address is a desert, and deserts distort the horizon. That is the disquieting insight the KBC void delivers. It does not simply add a new object to the catalogue of cosmic structures. It rewrites the catalogue's authorship. We have built our picture of the universe from inside a bubble that makes the local seem universal. The true cosmic average, the real density, the real expansion rate, the real distribution of galaxies, may be unknowable from this position. Not because our instruments are insufficient, because our location is wrong in a way no instrument can correct. The skepticism must be acknowledged. Some researchers argue the void is itself a phantom, an artifact generated by galaxy surveys that have not yet mapped enough of the sky with sufficient depth. The deficit of galaxies could be a deficit of data, not matter. The debate remains open, and every new survey, DESI, Euclid, the Rubin Observatory, will tighten the constraints. But the discomfort of the hypothesis does not vanish under scrutiny. If the void is real, the Milky Way's location is a statistical outrage that challenges structure formation models. If the void is not real, then our galaxy surveys are missing something fundamental, and the maps we trust are incomplete in ways we cannot yet quantify. Either fork leads to the same place. We are inside something we do not fully understand, and the thing we are inside may be distorting every measurement we have ever made. The emptiness is not a feature on the map, it is the map, and we cannot step outside to check how distorted our view truly is. So the void hypothesis rescues the Hubble tension from needing new physics. It does so by making a different demand. If the KBC void is real, then the Hubble constant we have measured from type Ia supernovae in our local volume, the number printed in textbooks, the number that tells us how fast the universe expands, is not the universe's number. It is a local reading, an artifact of thin space. Underdense regions expand faster. This is not speculation. Gravity from mass slows expansion locally. Remove mass, and expansion meets less resistance. Inside a void, the effective Hubble constant runs high. If the Milky Way sits inside the KBC void, then every supernova we have clocked within a few billion light-years has been exploding inside that same underdensity. The expansion rate we have derived from them is not wrong for our location. It is simply not the cosmic average. The Hubble tension is not a sign of new physics. It is a symptom of our address. That is where the vertigo begins. Standard candles, the objects astronomers use to measure cosmic distances, depend on an unspoken premise. Type Ia supernovae are bright enough to see across billions of light-years. Their peak luminosity is predictable because the physics of their detonation is consistent. A white dwarf accretes matter from a companion star, reaches the Chandrasekhar limit, and incinerates itself in a thermonuclear blast. That consistency makes them calibratable. You measure how bright a supernova appears, compare it to how bright you know it actually was, and the difference gives distance. The method is elegant. It is also dependent on a single assumption, that the space through which the light travels is representative. If our local volume is underdense by 20%, that assumption fails. The calibration itself, the translation from apparent brightness to absolute distance, was built inside the bubble. The ladder of measurement that stretches from parallax to Cepheids to Type Ia supernovae is anchored in a neighborhood that may be thinner than average. A tilted foundation. When you tilt the foundation of a ladder, every rung shifts. The true distance to the coma cluster. The true size of the observable universe. The true age since the hot, dense beginning. Every number inherits the distortion. The uncertainty is not a few percent. It is systematic. It is baked into every redshift to distance conversion, every Hubble diagram, every inference from the brightness of a dying star in a galaxy a billion light-years away. The permanent asterisk is this: we do not know which numbers to trust. The Hubble constant we measure locally, 73 kilometers per second per megaparsec, may be accurate for a sphere of space centered on us. The cosmic microwave background value, 67, may be accurate for the whole. The discrepancy is not an error. It is a measurement of how different our bubble is from the average universe. But we cannot confirm that from inside. We cannot take a telescope out of the void to read the background from neutral ground. No spacecraft will cross a billion light-years to bring back a comparison. The edge of the KBC void, if it exists, lies beyond the reach of every instrument we will ever build, every probe we will ever launch, every signal we will ever send. The expansion of the universe ensures that even if we aimed a beam at the boundary would recede faster than the signal travels. We are sealed inside. The bubble is all the data we will ever have. Skepticism must be noted. The KBC void may itself be an artifact, a feature not of the universe, but of incomplete galaxy surveys. A phantom generated by mapping a patch of sky that is not yet fully catalogued. Some astronomers argue the deficit is a deficit of data, not mass. The surveys that will tighten the constraints, DESI, Euclid, the Vera Rubin Observatory, are still unfolding. The question remains open. But if the skeptics are wrong and the void is physically real, the demand on cosmology is severe. Standard structure formation models must explain why a void this large exists. They must explain why we are near its center, a statistical discomfort that does not disappear with better data. The models produce large voids. They do not easily produce voids of this scale with bright spirals parked near the center. That is not a comfortable anomaly. It is a crack in the logic of cosmic structure formation, and the crack does not close with more data. If the void is real, the models must account for the fact that a region so empty should not have produced a galaxy like ours in its interior. And if the void is not real, if the deficit dissolves under deeper surveys, then the maps we have trusted for decades are missing something fundamental, and we do not yet know what. Either way, the asterisk remains. The psychological weight lands when you consider what this asterisk actually means. Not the abstract debate, the numbers. The age of the universe, currently placed at 13.8 billion years, was calculated by integrating the expansion history backward from our local measurement of the Hubble constant. If that local measurement is inflated by 20%, the age shifts. The true age might be older or younger, depending on how the void's density profile smears the expansion curve. The acceleration of expansion, the discovery that earned a Nobel Prize in 2011, was inferred from the brightness of distant supernovae, compared to nearby ones. If the nearby ones sit in an underdensity, the contrast is exaggerated. Dark energy might be weaker than we think, or stronger, or not a constant at all. The distribution of dark matter, mapped through gravitational lensing, depends on knowing the distances to the lens and the source. Wrong distances, wrong map. We have been studying a pond and calling it the ocean. The standard candles themselves, the Type Ia supernovae, are not immune. Their calibration rests on a chain. Parallax measurements of nearby stars anchor the Cepheid period luminosity relation. Cepheids anchor the supernovae. Each rung of that chain sits inside the local volume. If the local volume is underdense, then every rung is calibrated in thin space, and the entire ladder is leaning. The Hubble constant is not the only number that shifts. The luminosity of a supernova, the inferred distance to its host galaxy, the expansion history written across billions of years. All of it is written in ink that dissolves under the void hypothesis. The hard truth is that we may never correct the bias. The edge of the KBC void, if it exists, lies roughly 1 billion light-years away. Even if we launched a probe today at near-light speed, the expansion of the universe would push that boundary outward faster than the probe could close. No measurement from inside can distinguish local underdensity from global average without an external reference that we are physically barred from obtaining. We are stuck with a biased instrument, our own region of space. And the bias is not a minor calibration error that can be modeled away with clever statistics. The bias is the sample itself. We have one universe, and we are inside it, and the piece we inhabit may be the wrong piece. The Hubble tension is not a problem waiting for a solution. It is a mirror. It shows us that our most fundamental measurements are fragile in a way that cannot be repaired. The void is not a distant object like the Boötes chasm. We breathe it. Every photon of extragalactic light that lands on our mirrors has passed through its thin fabric. The lens is curved, and we cannot take it off. The picture we have built, of expansion, of acceleration, of the fate of the cosmos, may be a provincial misinterpretation. The universe we think we know may be a local illusion, permanently sealed from correction by the geometry of our own emptiness. That is the final weight the KBC void deposits. Not a new theory, not a tidy resolution, but a permanent crack in the foundation of every cosmic assertion. We cannot step outside the bubble. We cannot recalibrate from neutral ground. And so the asterisk will remain, stamped silently next to the Hubble constant, next to the age of the universe, next to the map of dark matter, and the forecast of our ultimate fate. The glass we look through is warped by the very space we occupy, and the distortion is not a temporary setback. It is the condition of being here. We may never know how much of what we see is the universe, and how much is the bubble breathing its thin, distorting breath across every photon that reaches our mirrors. We are sealed inside, and the only number we cannot measure is the one that would tell us how wrong we have always been. In 2013, the same year the KBC void first appeared in the literature, a different team was looking at a different kind of emptiness. They were not counting galaxies. They were counting explosions. Gamma-ray bursts are the most violent events in the known universe. In a few seconds, a single burst releases more energy than the Sun will produce in its entire 10 billion-year lifetime. They are born when massive stars collapse into black holes, or when neutron stars spiral together and merge. And because they are so bright, briefly outshining entire galaxies, they can be seen across almost the entire span of the observable universe. That makes them perfect tracers of the largest structures. Where galaxies cluster, gamma-ray bursts should cluster too. The map should reflect the web. Istvan Horvath and his colleagues were building that map. They gathered data on several dozen bursts detected by multiple satellites, each one localized with enough precision to assign a distance. The distances were immense, billions of light years, stretching back toward the early epochs of star formation. They plotted the bursts in 3 dimensions and began to look for patterns, for the filaments and clusters and voids they expected to find. What they found instead stopped them cold. The bursts were not scattered. They were not tracing the gentle foam of the cosmic web. A tight knot of them, more than a dozen, sat clustered in one region of the plot. Their redshifts were nearly identical. Their separations in space were far smaller than chance would allow. Horvath stared at the screen and spoke the words that would define the next decade of structural cosmology. "Look at this! They're all in one place. Over a dozen bursts, and the separation in redshift is less than 0.01. That's impossibly close. That means they're all part of one structure." The structure stretched across nearly 10 billion light years, 10% of the diameter of the entire observable universe, in a single coherent chain of galaxy clusters and gamma-ray burst hosts. They named it the Hercules Corona Borealis Great Wall. 10 billion light years is not a number that fits comfortably inside the mind. The Milky Way is 100,000 light years across. Laniakea, the supercluster that reduced our galaxy to a dot on a map, spans 500 million. The Great Wall would swallow 20 Laniakeas end to end. If it is real, it is not merely the largest known structure in the universe. It is a structure at the hard limit of what standard cosmology says should exist. That limit is the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic, smooth and uniform in every direction. Zoom out far enough, and all the clumps and clusters and filaments should average into a featureless field. The principle is not a philosophical preference. It is the foundation on which the standard model of cosmology rests. The Friedman equations that describe cosmic expansion, the predictions of Big Bang nucleosynthesis, the power spectrum of the cosmic microwave background, all of them assume that no structure dominates the universe when you look at scales beyond a few 100 million light years. A 10 billion light-year wall violates that assumption. It is not a mild anomaly. It is a scar across the face of uniformity. If the Great Wall is a genuine physical superstructure, then the universe is not smooth on the largest scales. It is lumpy. And the lump is so large that our entire model of how structure formed from primordial quantum fluctuations cannot easily accommodate it. The cold dark matter paradigm, with its nearly scale-invariant initial conditions, does not casually produce coherent chains of galaxies that span a tenth of the observable universe. To produce such a thing, the initial conditions would have to be far from Gaussian or some exotic physics. Cosmic strings, topological defects, something outside the standard framework would have to be at work. The alternative does not rescue us. Horvath himself was the first to voice it. After the initial shock of the clustering, he paused and said, "It might not be real. It might be a statistical ghost, a trick of the eye in a very small sample." The sample was indeed small. Gamma-ray bursts are rare, and only a fraction are localized well enough to place in a three-dimensional map. When you are working with a few dozen points scattered across most of cosmic history, the chance of a false clustering is not zero. Unrelated bursts at different distances can align along the line of sight. Their redshifts may overlap by accident rather than by physical association. What looks like a wall can be a projection artifact, a phantom created by the limited depth perception of our instruments. That is the second possibility. The Hercules Corona Borealis Great Wall is not a structure at all. It is a mirage, a trick of perspective in a sparse dataset. The largest object ever mapped is not an object. it is a ghost. Now consider the position you are left in. Both possibilities are real. Both are supported by reasonable arguments. And both are, in their own way, a kind of horror. If the wall is physically real, then the cosmological principle is false. The universe is not uniform. It is built from structures so immense that they break the mathematics we have relied on for a century. The smoothness we see in the cosmic microwave background, the oldest light, the supposed evidence of a simple and orderly beginning, must be reconciled with a present-day cosmos that is grotesquely lumpy. That reconciliation is not available. The models do not stretch that far. If the wall is not real, if it is a statistical ghost, then our most ambitious maps are unreliable. The tools we use to trace the cosmic web, the gamma-ray bursts and galaxy surveys and redshift catalogues, can produce phantom structures that look convincing but are nothing at all. The Hercules Corona Borealis Great Wall is not an isolated case. Other large structures have been proposed and debated. The Sloan Great Wall, the giant GRB ring. Each one sits at the edge of statistical significance, haunting the maps like faces in clouds, never quite resolving into proof, never quite fading into noise. The Hercules Corona Borealis Great Wall is the most extreme of these apparitions, and it shares their condition. It is undecidable. We cannot gather more gamma-ray bursts to sharpen the picture because the events are too rare. We cannot confirm the structure in visible light because the galaxies that would mark it are too faint at those distances. The wall sits at the edge of our instruments and at the edge of our logic, occupying the exact space where data gives out and interpretation begins. That is where the true spectral horror lives. Not in the scale, not in the breaking of the cosmological principle, but in the permanent structural inability to know whether the largest thing we have ever mapped is a thing at all. A real wall of 10 billion light-years means the universe is not what we thought it was. A ghost means our methods for mapping cosmic architecture are not what we thought they were. Both futures leave the same silence behind them. Both remove solid ground. And there is no third future in which the wall resolves into something safe. The Hercules Corona Borealis Great Wall stands as a monument to uncertainty, the largest known candidate in physical reality that may be nothing but a pattern glimpsed in smoke. It may be real and universe-breaking. It may be a statistical echo of our desperate need to find structure in the dark. Either way, it does not give us answers. It gives us a question that cannot be closed. And that denial of resolution, that permanent suspension between two unlivable worlds, is the real terror the wall deposits. It is not a discovery. It is a crack, and light does not come through. The great attractor is not the deepest current. It is merely the deepest one we can map. Beyond it, beyond the Norma cluster, beyond the filaments of Laniakea, beyond the 93 billion light-year bubble that contains everything we will ever see, some surveys have detected motion that should not be there. The signal is called dark flow. It emerged not from images but from velocities. Astronomers measured the movement of hundreds of galaxy clusters against the cosmic microwave background, the oldest light in existence. Most clusters moved as expected, toward local attractors, toward filament intersections, toward the gravitational centers the maps predicted. But a fraction moved in a common direction. They showed a coherent bulk motion, a flow, pointing toward a single patch of sky far beyond the limits of our observable universe. If the signal is real, then entire clusters of galaxies, each containing thousands of galaxies, each galaxy containing hundreds of billions of stars, are being pulled, not by the great attractor, not by any structure that lies within the sphere of our causal access, by something outside everything we can ever observe. The direction points toward the constellation Centaurus and Vela, but the attractor itself lies beyond the cosmic microwave background surface, beyond the edge where light itself was released. We cannot see it. We can never see it. The observable universe is a causal bubble. Its edge is not a wall in space. It is a horizon in time. The surface where the expansion of space carries objects away from us faster than light. Beyond that horizon, by the fundamental laws of physics, no signal can reach us. No light, no gravitational waves, no transmission of any kind. The boundary is absolute. The region beyond is not merely distant, it is causally severed from our reality. A dark flow pointing toward that boundary means something on the other side has enough mass, enough gravitational authority to reach across the severance and tug at the fabric of our universe. We cannot observe it. We cannot confirm its nature. We cannot even prove it exists by any direct method. We can only watch the clusters move and infer that something is there. Conflicting studies have torn at this signal for years. Some analyses find no significant flow. They argue that the motion is a statistical artifact, a ghost created by incomplete cluster catalogues, by biases in how velocities are measured, by the uneven distribution of data across the sky. When certain clusters are removed, the flow weakens. When different methods are applied, it vanishes. The most cautious astronomers dismiss it entirely. But not all of them. Other studies, using independent data sets and different statistical treatments, continue to detect the flow. They find it at similar strengths and in similar directions. The debate remains unresolved, and its very structure is a kind of torture, because we can never settle it. To confirm a dark flow would require measuring the thing that causes it, and that thing lies beyond the horizon, permanently inaccessible. To refute it would require proving a negative across a data set that will always be incomplete. The question is not merely unanswered. It is undecidable. It sits in the exact space where evidence gives out and conviction must take over. And conviction is not a tool of science. We are left in a condition of permanent epistemic suspension. We cannot dismiss the possibility that we are being dragged toward a structure outside our reality. We cannot confirm it. The flow either exists or it does not, and we will never know which world we inhabit. This alone would be enough. But the cosmic microwave background, the oldest light, the afterglow of the Big Bang itself, contains a second anomaly that presses against the same boundary. The CMB should be almost perfectly uniform. The temperature of the radiation, released 380,000 years after the beginning, varies by less than 1 part in 100,000 across the entire sky. Those tiny variations are the seeds of all later structure, the quantum fluctuations stretched to cosmic size. They are well understood and well mapped. But there is one feature that does not fit. The cold spot, a patch of sky roughly 10 degrees across, 20 full moons wide, that is unusually cold. The temperature dip is not enormous in absolute terms, roughly 70 microkelvin below the average, but it is significantly larger and colder than the standard model predicts for a random fluctuation in a Gaussian field. Explanations have accumulated. It may be a statistical fluke, the inevitable extreme outlier in a sky that we have examined at every scale. It may be the imprint of a giant foreground void, the Eridanus supervoid, a region of below-average density, nearly 2 billion light-years across, that sits between us and the cold spot, cooling the CMB photons as they pass through by the integrated Sachs-Wolf effect. Neither explanation is wholly satisfying. The void is large, but not large enough to account for the full amplitude of the cold spot. The statistical fluke is possible, but the probability is low. And then there is the third possibility, the one that lives outside the standard model entirely. Some cosmologists have proposed that the cold spot is a scar. the imprint of a collision between our universe and another bubble universe in a larger multiverse. In eternal inflation models, our universe is one bubble among an infinite froth of bubbles, each with potentially different physical constants, each born from a separate nucleation event. If two such bubbles collided in the earliest moments, before inflation had fully separated them, the impact would leave a mark in our CMB, a cold region, a bruise in the oldest light. No consensus exists. The hypothesis is highly speculative, untestable by any direct means, and rejected by most researchers. But the fact that it can even be proposed that the best maps of the earliest universe contain a feature for which a collision with another reality is a legitimate candidate explanation, reveals how little ground we are standing on. The cold spot may be a ghost in the noise, a foreground void, or a scar from outside everything we can access. We do not know. We may never know. The dark flow and the cold spot are not separate mysteries. They are apertures onto the same abyss. Dark flow suggests something beyond the horizon is pulling at the fabric of clusters. The cold spot suggests something. Perhaps the same category of something, perhaps not. Left a bruise on the oldest light we can see. Both point toward a region of reality that is causally amputated from our own. A direction we can never follow, a past we can never interrogate. We are sealed inside a bubble of causal access, and the bubble is all we will ever know. The horizon is not a temporary frontier awaiting better telescopes. It is a fundamental feature of the geometry of space-time. Accelerating expansion carries everything beyond that boundary away from us faster than light. The signals from whatever lies there, light, gravity, information of any kind, will never arrive. They are not delayed. They are lost. The deepest truths about where we live may be written beyond the visible edge. What built the attractor that pulls us? What collided with our universe in its first moments? What scars exist in the oldest light that we cannot distinguish from noise? These questions are not merely unanswered. They are unanswerable. Not because we lack cleverness. Because the universe was built to deny us the evidence. That is the true horror. Not the darkness itself. Not the cold. Not the isolation. The permanent condition of being locked out of the answers that matter most. We can infer. We can speculate. We can build models of multiverses and colliding bubbles and attractors beyond the causal wall. But we can never test them. We can never know. The thing that pulls us, the thing that scarred our beginning, is not hidden behind a locked door. The door does not exist, and so we are left with hints that will never resolve into proof. Motions we cannot explain, temperatures we cannot account for. A universe that seems, at its very edges, to be in contact with something we are forbidden to see. The dark flow and the cold spot are not discoveries. They are symptoms of a boundary that is both physical and epistemic, a limit not just of what we can reach, but of what we can mean. What pulls us? What scarred the oldest light? The answers exist or they do not. Either way, we are barred from them. That is the permanent nausea, the queasy certainty that the cosmos is larger than our capacity to interrogate it, and that the most important forces shaping our motion and our history may be forever outside the circle of our knowledge. We will never turn the page. The Fermi paradox is usually framed as a question about probability. The universe is old and full of stars. Planets are common. The raw materials for life appear everywhere we look. So, where is everybody? The question assumes something it should not. It assumes the galaxy field is rich and evenly sown. It assumes the universe is a crowded room where silence is suspicious. But we have spent the preceding sections of this journey mapping a different truth. The universe is not a crowded room. It is a foam, and we live in one of the bubbles. The cosmic web revealed by the Sloan Digital Sky Survey and decades of redshift mapping is not a uniform distribution of galaxies. It is a three-dimensional network of thin filaments and dense knots, the walls and intersections where galaxy clusters gather. These filaments and clusters occupy roughly 5% of the universe's volume. The remaining 95% is void, not dilute, not sparse, void. Regions where galaxy formation was suppressed before it could begin, where the average distance between galaxies dwarfs anything in our local experience, where a civilization could look out and see nothing but darkness in every direction. The natural density of advanced life, if it exists anywhere, would not be spread evenly across this architecture. It would be concentrated in the 5%, the star-rich filaments, the dense knots around attractors, the great walls where galaxies cluster by the thousands and star formation runs hot and continuous. Our address is not in that 5%. The local group is a minor collection of approximately 50 galaxies on the periphery of the Laniakea supercluster. The Milky Way sits in a filament on the outer edge, not in the dense core. And we may sit inside a void, the KBC void, a 2 billion light-year underdensity, where matter thins to 20% below the cosmic average. If that void is real, our region of space is not typical. It is a cosmic backwater in a universe where backwaters are the dominant geography. Now consider what this does to the silence. If life concentrates in the great filaments, the Hercules Corona Borealis Great Wall, the dense knots feeding into the great attractor, the major cluster intersections that light up with star formation, then those regions are not close. They are not even distant in the conventional sense. A filament 1 billion light-years away contains civilizations whose earliest radio signals, travelling at the speed of light since the Cambrian explosion on Earth, would be arriving only now, and we could not hear them. A billion-year-old signal stretched by cosmic expansion would be redshifted into near indecipherable noise, its power diluted across a volume of space that defies recovery. The message would not be a message. It would be a whisper buried in static, indistinguishable from the background hiss of the cosmos. Even that assumes the signal was sent when it was. But civilizations are not permanent. They rise and fall on timescales we cannot predict. A signal from 1 billion light-years away is a snapshot of their past, a moment that may have extinguished long before the light reached the halfway point. And by the time any reply could be formulated here and sent back, cosmic expansion would have already dragged the source beyond our event horizon. The horizon is the final filter. The accelerating expansion of the universe does not just stretch distances. It severs causal contact. Every day, galaxies near the edge of our observable bubble cross a boundary from which no signal can ever return. The geometry of space-time itself walls them off. If the most densely populated filaments lie near or beyond that boundary, or if they will cross it in the time it takes a signal to travel, then the silence is not evidence of absence. It is evidence of amputation. The voices exist, or they once did, but the universe has already decided we will never hear them. This is not the great filter of standard Fermi discourse. The idea that some catastrophe destroys civilizations before they can spread. This is a shape filter, a structural filter. The filter is not a predator, or a plague, or a self-inflicted extinction. It is the architecture of the cosmos itself, 95% empty by volume, 5% too far to reach. The silence is not a puzzle waiting for an explanation. It is the expected acoustics of living in a foam bubble, surrounded on all sides by hollow distance. Carl Sagan's line from Cosmos returns with its meaning inverted. The universe is a pretty big place. If it's just us, seems like an awful waste of space. But the emptiness is not wasteful. It is functional. It is the barrier. The space between the filaments is not there to be filled. It is there to separate, to isolate, to ensure that the islands of structure never touch. The waste is not a design flaw, it is the design. If the Milky Way sits inside the KBC void, then our star density is lower than the cosmic average. The raw material for planet formation, for complex chemistry, for the long, slow burn of biological evolution. All of it is thinner here than in the dense filaments. Our region is not a likely host for multiple independent emergences of intelligent life. It is a cold desert where a single fire caught. We may be that fire, not because the universe forbids others, but because our neighborhood was never rich enough to kindle more than one. The Fermi paradox has spawned a library of solutions. They self-destruct. They upload themselves into simulations. They are hiding. They are sleeping. They are so alien we cannot recognize their signals. Each of these proposals imagines agency, that someone out there is doing something that explains the quiet. But the cosmic web offers a bleaker resolution. No one needs to do anything. The silence is not a choice made by civilizations. It is a property of the address they inhabit. Most addresses in this universe receive nothing. They are voids. They are sparse filament edges. They are bubbles in a foam where the nearest populated walls lie beyond a distance that light, even racing at 186,000 miles per second, cannot cross before the expansion of space makes the crossing infinite. We are not hearing silence because the room is empty. We are hearing silence because we are in the wrong part of the building, and the walls are thickening, and the doors have already closed. The sound of a void is not a lack of noise. It is the acoustic signature of an architecture built from absence. The only fire in a cold desert hears nothing but its own burning. That is not a mystery. That is a location. The oldest light in the universe was released 380,000 years after the Big Bang. It is called the cosmic microwave background. It should be nearly uniform, a smooth wash of ancient photons cooling as space expands, varying by no more than 1 part in 100,000 across the entire sky. That prediction is one of the tightest in all of cosmology, and it is wrong. The Wilkinson Microwave Anisotropy Probe, WMAP, mapped the cosmic microwave background between 2001 and 2010. Its successor, the Planck satellite, refined that map to a precision that left nowhere to hide. Both found the same anomaly. A patch of sky in the constellation Eridanus, roughly 1 billion light-years across, that is colder than it should be, not by a small margin. The temperature depression is about 70 microkelvin, deeper than the average fluctuation at that scale. That number sounds small, but on a map where variations are measured in tens of microkelvin, it is a wound. They named it the CMB cold spot. The standard explanation is that it is a statistical fluke. In any random field the size of the microwave sky, some regions will dip lower than others. The cold spot might be nothing more than a chance arrangement of primordial photons, no more meaningful than a face seen in clouds. A second possibility is that it is a foreground effect, a giant void sitting between us and the surface of last scattering, whose underdensity imprints a cold shadow through the integrated Sachs-Wolf effect. If such a void exists, it would be one of the largest structures ever inferred, and we would be looking through it as we look back to the beginning. Neither explanation is comfortable. The void hypothesis requires a structure so immense that it strains the standard model of structure formation. The statistical fluke hypothesis requires us to accept that the most prominent anomaly in the oldest light we possess is just noise, that the universe's birthmark is illegible in the one place we most want to read it. Then there is the third possibility. Some cosmologists have proposed that the cold spot is a scar, a bruise left by a collision between our universe and another bubble universe in a larger multiverse. The idea comes from eternal inflation. The theory that the inflationary epoch that birthed our observable patch never stopped and continues to generate an infinity of other bubble universes with different physical constants, different histories, different fates. In this picture, our universe is one bubble among uncountably many, expanding into a larger inflating medium. Occasionally, bubbles collide. When they do, the boundary between them radiates energy, a ring of distorted space-time, a gradient in the density of matter, a signature in the cosmic microwave background, something that would look, from the inside, like a cold spot. No consensus supports this hypothesis. No confirmed second signal corroborates it. The cold spot could be a ghost in the data, a coincidence amplified by our pattern-hungry brains. But the fact that the hypothesis exists at all, that respected physicists can look at the oldest light, see a depression 70 microkelvin deep, and seriously propose that it came from outside everything we can ever access, tells you something about how little we can rule out. We cannot step outside to check. The observable universe is a sphere 93 billion light-years across. That is not a sky. That is the limit of causal access. Light from beyond that boundary has not had time to reach us in the 13.8 billion years since the Big Bang, and thanks to the accelerating expansion of space, it never will. The boundary is not a wall in space, it is a horizon in time. Every galaxy, every photon, every gravitational wave originating beyond it is carried away from us faster than light. Not moving through space faster than the speed limit, but riding the expansion of space itself, which obeys no speed limit. The horizon recedes, but it recedes into a future we cannot catch. We are sealed inside a bubble of causal access. The bubble is all we will ever know, not all that exists, not all that could be measured from a different vantage point, but all that can ever interact with us, influence us, be confirmed by us. The rest is not hidden by darkness or distance. It is hidden by the fundamental structure of reality. This is not a temporary ignorance. It is not a puzzle that better telescopes or faster spacecraft will solve. It is a permanent condition. The laws of physics themselves draw the line between what we can know and what we cannot, and they draw it at 93 billion light-years. The cold spot, if it is a scar, is a mark from beyond that line, a signal from a region that has already receded past the horizon, that no future observation will ever resolve, that we can only interpret in whispers and maybes. The scar, if it is real, is not a clue we can follow. It is a reminder that the walls exist. Radical cosmologies flourish in this epistemic vacuum. Some models propose that the universe is finite and multiply connected. A torus, a dodecahedron, a shape that wraps back on itself, so that light from a single galaxy could travel in a loop and arrive at Earth from multiple directions. If the universe is small enough, we could in principle see the same galaxy in opposite parts of the sky, its light having circumnavigated the cosmos. Searches for these repeating patterns have found nothing conclusive. The scale of the topology, if it exists, must be larger than the observable horizon, which means it is untestable. Eternal inflation spawns a multiverse with different physical constants in every bubble, some hostile to structure, some perhaps teeming with life governed by physics we cannot imagine. The string theory landscape posits 10 to the power of 500 possible vacuum states, 10 to the 500 different ways the fundamental constants could be set. Our universe would be one valley in an incomprehensible mountain range. The hypothesis is mathematically rich. It is also immune to falsification. We can never visit another bubble. We can never measure another set of constants. We can only infer from the one sample we have, and the sample is sealed. Then there is the infinite universe, space extending forever, with more stars, more galaxies, more voids, more filaments, an eternal recurrence of structures never exactly repeated. That model is the most conservative. It is also untestable. We cannot observe infinity. We can observe the 93 billion light years we are permitted to see, and we can extrapolate. Extrapolation is not proof. The radical cosmologies form a catalogue of unknowable truths. Finite toruses, colliding bubbles, vibrating strings in a landscape of 10 to the power of 500 false vacua. A universe that loops back on itself so that the same galaxy could appear in multiple directions. A multiverse that branches with every quantum measurement. These are not fringe speculations from the edges of science. They are the direct offspring of our best theories, pushed past the point where evidence can follow. They all share a single property. None can be falsified from inside this bubble. We are trapped not just by distance, but by the architecture of reality itself. The deepest truths about where we live may be written beyond the visible edge, in a region that recedes faster than any signal can travel. Every map we make of the cosmic microwave background, of galaxy clusters, of the largest filaments and deepest voids, is a map of a prison cell. The walls are not steel, they are geometry. And we cannot break them, we cannot even see them. We can only infer their existence from the cold spot, from dark flow, from the hints that something is out there pressing against the boundary of our access. The scar of the unknown is not a mark on the sky. It is a condition of existence. The universe grants us questions without answers, hints without confirmations, suspicions without verdicts. Not because the answers do not exist, not because we are not intelligent enough to find them, but because the structure of space-time was built this way. The horizon is not a temporary obstacle. It is a permanent amputation of knowledge. We will die asking the same questions we ask now, and those questions will remain as open then as they were the moment the first human looked up and wondered. Now, assemble the mosaic. We occupy a minor filament on the periphery of the Laniakea supercluster, inside what may be a 2 billion light-year underdensity called the KBC void. The universe, by volume, is 95% hollow. We are falling toward the great attractor at 600 kilometers per second, 2 million miles an hour, toward a hidden gravitational center whose pull may not be gravity alone. The largest structures we have mapped may be physical impossibilities or statistical ghosts. Forces beyond our observable horizon may be dragging entire clusters of galaxies towards something we will never see. The cold spot in the oldest light may be a scar from a collision with another universe. These are not separate discoveries. They are a single condition, seen from different angles. The notion of place collapses at this scale. The words vast and tiny become noise. Sounds we make to fill the silence while the real architecture sits indifferent to our categories. The Milky Way is not a galaxy adrift in open space. It is a rounding error in a network that extends not just beyond our galaxy, not just beyond our supercluster, but beyond our observable universe. The 100,000 light years of our home spiral, the 200 billion stars, the entire local group with its 50-odd galaxies, all of it is a single pixel in an image whose full dimensions we cannot capture, because the image extends past the frame of what physics permits us to photograph. We are not the center. We are not the outskirts. We are a fleeting condensation in a bubble, a temporary pattern in the foam that thinks it is a nation. This demands a renegotiation of every story we tell about the future. Expansion across the galaxy, contact with other intelligence, mastery of the cosmos. These are not ambitions. They are category errors. We have mistaken our foam speck for a stage. The stars we see at night are the exception, not the rule. Most of space is an absence where nothing shines. Most of space is an absence where nothing has ever shone, and nothing will ever shine. because galaxy formation was suppressed in those regions before it could begin. The dark patches between constellations are not gaps waiting to be filled. They are the default condition. We are the aberration. Contact with other life must be renegotiated against a cosmic web, where intelligent species, if they exist, are likely concentrated in the dense filaments, the 5% of the universe's volume that is star-rich. Those filaments are unreachable, not difficult to reach, uneachable. The accelerating expansion of space carries them beyond our event horizon faster than any signal can travel. Even if a civilization in the Hercules Corona Borealis Great Wall broadcast a message at the speed of light, the space between us stretches faster. The signal will never arrive. The geometry of the cosmos does not permit the conversation. Mastery of the cosmos must be renegotiated against a causal boundary 93 billion light-years across, beyond which no observation, no experiment, no instrument can ever penetrate. We cannot master what we cannot measure. We cannot measure what lies beyond the horizon. The horizon is not a temporary obstacle. It is a permanent wall built into the structure of space-time. We will never know what sits beyond it. We will never confirm whether dark flow is real. We will never resolve whether the cold spot is a scar or a fluctuation. We will die asking the same questions we asked the moment we first understood there was a beyond to ask about. And yet, the legacy of this knowledge is not despair. Despair requires the universe to have wronged us. It has not. The cosmic web does not hate us. It does not notice us. The Boötes Void is not malevolent. It is a region where formation failed, a consequence of quantum fluctuations in the first instance after the Big Bang. No intention shaped it. No force targeted the galaxies that never formed there. The absence is not a punishment. It is a statistic. The great attractor does not hunger. It does not reach out with gravitational fingers to drag us into its maw. It is a density, an overdense knot of galaxies and dark matter in the Norma cluster, sitting behind the zone of avoidance, exerting a pull that is simply physics. It does not know we are falling toward it. It does not care. The 600 kilometers per second of our motion is not a chase. It is a current. We are debris in a river that has no destination. The silence of the cosmos is not a message waiting to be decoded. It is the acoustic signature of an architecture built from absence. If other voices exist, they are in the filaments, and the filaments are receding. We are not being ignored. We are separated by the geometry of an expanding universe that treats empty space as its default and clustered matter as a rounding error. The silence is not from them. It is from the void itself, the permanent structural quiet of a cosmos that is 95% hollow. This is the pivot, and it is the hardest one to make. Cosmic fear, the genuine bone-deep dread that these scales can evoke, is not about alien invasions. It is not about gamma-ray bursts sterilizing the galaxy. It is not about extinction from the sky. It is the creeping realization that the universe never needed us. It did not need stars or galaxies or the delicate carbon chemistry that produced our consciousness. It did not need the local group, or Laniakea, or the Great Wall. It had no purpose that our existence fulfills. The emptiness is not hostile, it is indifferent. Indifference is far worse than hostility. Hate requires attention. Malice requires a target. The cosmic web is not malicious. It simply does not register us. We are not an enemy to be defeated. We are not a threat to be neutralized. We are background noise in a story that was never about us. And yet, this is not an insult. It is a release. The universe does not demand our significance. It does not mourn our absence. The Boötes Void will not fill with galaxies to correct the deficit. The great attractor will not complete its pull and reveal a final destination. The dark flow, if real, will never resolve into a visible attractor. The cold spot will remain a cold spot. a 70 microkelvin depression in the oldest light, forever indecipherable. These are not mysteries that wait for our telescopes to grow sharper. They are permanent features of our condition. We are not at the center of a grand drama. There is no grand drama. There is a foam of baryonic matter and dark matter, stretched into filaments and walls by gravity and expansion, threaded with hot gas that will never cool into stars, pocked up with voids that will never host a single civilization. The Milky Way is a condensation in one filament, a temporary clumping of hydrogen and helium and heavier atoms that briefly ignited, briefly thought, briefly mapped the walls of its own bubble before realizing the bubble was all it would ever know. A glitch in the pattern of emptiness, a flicker. The bubble will continue to expand. The attractor will continue to pull. Our galaxy will continue its silent fall toward the Norma cluster, never arriving, because the space between us and it stretches faster than we can cross. Long after our voices fade, long after the sun swells and swallows the inner planets, long after the local group merges into a single elliptical corpse, the voids will remain voids. The filaments will stretch and thin. The cosmic web will redden into a sparse skeleton of dead galaxies, and the 95% hollow that was always the default will become the entire sky. And the void will remain the void, not because it won, not because it consumed us, but because it never needed us in the first place. The emptiness is not an enemy. It is the baseline. We mistook a temporary condensation for a permanent edifice, a fleeting bubble for a foundation. This is not despair, it is clarity. The terrifying truth about what lies beyond the Milky Way is not that it is empty. It is that the emptiness was always there, and always will be, and we were the exception that mistook itself for the rule. The Boötes Void is not a distant whole. That is the first thing to understand as the mosaic assembles. In 1981, when Robert Kirshner and his colleagues found a patch of sky the size of a full moon with almost no galaxies in it, they were not discovering a place far away. They were finding a mirror. The whole they mapped, 330 million light-years of near-total emptiness, 60 galaxies where thousands should burn, is the same kind of place we might already inhabit. The KBC void, proposed in 2013 by Keenan, Barger and Cowie, is estimated at 2 billion light-years across. Matter density inside it runs 20% below the cosmic average, and the Milky Way sits near its centre. If this void is real, and the evidence, though debated, has not been dismissed, then Kirshner's hole in the universe is not a curiosity on the edge of the map. It is the map. We are inside the thing he described. We did not notice because we were born inside it and have never seen anything else. The thinness of our local cosmos is the only texture we know. The emptiness that feels so viscerally wrong when you stare at a map of the Boötes Void, that ache of looking at a region where formation itself failed, is not something we observe from a safe distance. It is the medium we breathe. Our air is under density, our horizon is a bubble wall, and we have never stepped outside it. The great attractor pulls us toward a phantom, 600 kilometers per second, 2 million miles an hour, toward a hidden knot of galaxies and dark matter that sits behind the zone of avoidance, permanently obscured by the dense plane of our own galactic disk. The pull may be gravity alone. It may not be. Stacey McGaw's 2019 measurements at Parkes Observatory hinted at increasing acceleration, something beyond the steady tug of a fixed mass. But we will never know. The attractor will never resolve. We fall toward it and never arrive, because cosmic expansion stretches the space between faster than we can cross. Dark flow, the controversial signal that entire clusters of galaxies are moving coherently towards something beyond our 93 billion light-year horizon, may be a statistical ghost. It may be real. The cold spot in the cosmic microwave background, a 70 microkelvin depression in Eridanus, may be a foreground void, a statistical fluke, or the scar of a collision with another universe. No consensus exists. None is coming. These are not separate terrors. They are the symptoms of a single condition. We are entombed in a bubble of nothing, and the bubble is all we will ever know. The causal horizon is not a temporary obstacle we will eventually pierce with better instruments. It is a permanent wall built into the structure of space-time. Beyond it, by the very laws of physics, no signal can ever reach us. Whatever sits out there, another universe, a larger multiverse, an infinite extension of the same cosmic web, is not just unknown, it is fundamentally unknowable. We will die asking the same questions we asked. The moment we first understood, there was a beyond to ask about. The silence of the cosmos is not a message waiting to be decoded. We have searched for that message for decades. We have pointed radio dishes at nearby stars and listened for patterns in the noise. We have scanned for megastructures, for waste heat, for the spectral fingerprints of industrial atmospheres. Nothing, and the cosmic web explains why nothing is the only rational answer. If other voices exist, they are in the dense filaments, the 5% of the universe's volume that is star-rich. Those filaments are not merely distant, they are receding. The accelerating expansion of space carries them beyond our event horizon faster than any signal can travel. We are shouting into a void that consumes every signal, and we always have been. The silence is not from them. It is the permanent acoustic signature of an architecture built from absence. This is the reversal that makes everything else click into place. The stars we see at night are the exception. The darkness between them is not an interruption in the pattern. It is the pattern. Most of space is an absence where nothing shines. Most of space is an absence where nothing has ever shone and nothing will ever shine, because galaxy formation was suppressed in those regions before it could begin, stifled by the same quantum fluctuations from the earliest moments of the universe that seeded overdensities elsewhere. We mistook a temporary clustering for the structure of reality. We took a crowded foam speck for a populated universe. The terrifying truth about what lies beyond the Milky Way is not that the universe will become empty. It is that the universe has always been empty. The emptiness is the baseline. The silence we thought was a message to decode is just the sound of where we live. We have already been swallowed by the void. Not recently, not as a future event we can avert. We were born inside it, and the journey through these facts has been the slow, cold recognition of our own address. Every map we made, every distance we measured, every signal we strained to hear. They were all drawn from the bottom of a hole we did not know we occupied. There is no rescue, no exit, no unfolding revelation that will restore our significance. The filaments that contain the dense, living regions of the cosmos are receding beyond our causal reach forever. The great attractor will never resolve into a visible engine pulling us home. The cold spot will remain a 70 microkelvin depression in the oldest light, a scar that might be a bruise from another universe or simply a meaningless fluctuation. We will never know which, and that is not a tragedy. It is a condition. The Boötes Void is not hell. It is not malevolent absence. It is a region where formation failed, and our own neighborhood is a region where formation barely succeeded. The 95% hollowness of the universe was never an attack on us. It was never even an afterthought. It is the default, and we are the temporary condensation that mistook a flicker for an epoch. We are background noise in a story that was never about us. That is not an insult. It is a release. The universe never demanded our significance. It will not mourn our silencing. The bubble will continue to expand. The attractor will continue to pull. Our galaxy will continue its silent fall long after our voices fade, and the voids will remain voids. Not because they consumed us, but because they never needed us in the first place. The only silence is not from them. It is from us, finally understanding where we are.